So in this video, I just wanted to end up all of our quantum mechanics on the atom by looking at an overview of the periodic table. So now I just want to give you an overview of the rest of the periodic table. But let's just look for the case where we have just two electrons. You have two electrons. One is in the atom, one's at position R1 and the other one's at position R2. What's the Schrodinger equation? Well, the Schrodinger equation is now minus h bar squared all over 2m delta squared, remember this is in 3D, psi plus u for the first electron, say. It's a function of, say, R1. One of the electrons is at position R1, the other one's at position R2. So this is the Laplacian for particle 1, right here, times psi, plus minus h bar squared all over 2m del squared for position 2 psi plus the potential for particle 2 is at location R2 psi equals E total psi. You notice you only have one wave function, psi, for both particles. So psi, this one psi for a combination, this psi is a function of R1 is for one of the electrons, and position R2 is the other electron right here. Now, we could break this up into just a product of two right here, which is psi of, say, R1. This would be the individual wave function for just one of them. Maybe I'll put A right there, where A would be the four quantum numbers, the N, the L, the M sub L, and the M sub S, that's times the other one, which would be at location R2. Okay. So it's a single, so this thing right here, these are the single particle wave functions, but really when you work out Schrodinger's, it's one big psi right here. Now the probability of finding the electron 1 at position 1 and the electron 2 at position 2, the probability R1 and R2, we know that it's just this star this right here. So this is, remember, this is the probability amplitude of finding the first electron at position 1 and the second one at position 2. So this would just be psi star R1, R2 times psi, just like we did before, R1, R2. Or we could just say it's the magnitude squared. It's psi R1, R2 squared. Okay. So now we can say if the particles are identical, well now every electron is identical to every other electron. You cannot tell them apart. It's impossible. So all electrons are identical. All electrons are identical. That has a lot of meaning here, they're all identical, which means if I swap the two electrons, you wouldn't know the difference. So if I were to, the probability of R1, R2 should be the same as the probability of R2, R1. So since they're identical, if I just swap the two, I can't tell the difference right here. Well, if that's true, then this is equal to then if I just swap them right here. So this thing is the same as if I just swap, instead of R1, R2, this is R2, R1 squared. So the probability is the same right here. Well, if this is equal to this, that must mean that if I take the square root of both sides, that means that psi of R1, R2 is plus or minus this. Plus or minus psi of R2, R1. Well, if they're identical right here, usually when we say that this is equal to plus that, for the plus case, we call that the symmetric case, when this is equal to plus that. So if psi of R1, R2 is equal to the positive of the other one, psi R2, R1, we call that the symmetric case. Symmetric case. And if this one is equal to minus that, we call it the anti-symmetric. So psi R1, R2 is equal to minus psi R2, R1. We call that the anti-symmetric. Okay. Well, for the symmetric one, if this is a solution and that's a solution, they're both, then I have to combine the two to get the general solution. So that means psi for the symmetric would be a combination of these two right here. It could be either one right here. The electron could be here. Electron A could be here, electron B could be there, or B could be here and A could be up there. It could work out either way. So this is, and to normalize it, this would be the symmetric one. It would just be this plus this. Psi of R1, R2, plus psi R2, R1, right there. And if it's the anti-symmetric, it'd be this, I guess it'd be a minus because the other one's a negative. It would be this minus that one. So the psi anti-symmetric would be 1 over the square root of 2 psi R1, R2 minus psi R2, R1. Okay, well, and now I haven't brought in this right here. I can do, remember, psi R1, R2, I can break them up into these two. I'll just do that for these two right there. So this psi symmetric is 1 over the square root of 2. So this would be psi A of R1, psi B of R2, and then this would be minus psi A of R2, psi B of R1. Okay, and likewise this one over here, this anti-symmetric one, would be 1 over the square root of 2 psi A of R1, psi B of R2, minus psi A of R2, psi B of R1. Now, all of the states that are symmetric right here, these ones all have integer spin. These ones all have integer spin. The spin can either be 0, 1, 2, ... Remember, we gave these a name. We called them bosons. One of them being the photon. You remember the photon had a spin of 1 right here. These ones over here have half integer spins. 1 half, 3 halves, 5 halves, ... These ones we called fermions. These one would, well, this one, let me just put the photon would be 1 over here. All the force carriers would be over here. The electron, the proton, and so on. The muon, all of those are over here. Now, one thing you'll notice is if psi A and psi B have the same quantum numbers, that is, they have the same NL, M sub L, and M sub S, then these two will be equal. You'll see these two are equal, and you'll get 0. Well, you can't get 0 for this because, remember, the probability of finding it is psi star psi. So what this is saying is that no two electrons can share in the atom, can share the same, no two fermions in an atom, which are electrons, can share the same quantum numbers. We call that the Pauli Exclusion Principle. Exclusion Principle. Okay, over here, photons, they could all have, if they could all be in the one state right here, same quantum numbers, but not electrons in an atom right here. And that's why you have to build them up in shells. Otherwise, all the electrons would want to be down in the very bottom shell right here. Now, this is what you get for if it's 2 electrons, these are the ones we care about when we're in the atom because they're fermions right here. But what would this be if it was, say, 26 electrons? Maybe it's iron right here. What's this thing going to look like if it was 26 right here? Well, this term's going to get pretty big right here, this term right here. And the way you would calculate it is you'd say psi, the anti-symmetric one, if you had 26. So that means it would depend on R1, R2, R3, R4, R5, all the way out to R26. And you would do is you take 1 over the square root of 26 factorial. That's a pretty big number. 26 factorial. And then what you need to do is you have a matrix here. It'd be psi A for R1, psi B for R1, psi C all the way down, I guess it'd be all the way there, it'd be 26, whatever that is, psi K sub R1. Then the next line you'd have psi A of R2, psi B of R2 all the way down to psi K of R2. And then you just keep going all the way down till you have psi A of R26. Psi B of R20 all the way down to psi K of R26. You calculate this determinant. The determinant of that would give you this state for iron. You notice you'd never want to do this right here. This thing would be huge right here, but they have approximation techniques to do that right there. I'm just showing you how you would do that. This is called the Slater determinant. Okay. Now, usually, if you look at the periodic table, they usually give you the atom ground states are characterized by the notation, by the number of electrons in each shell. You'll notice they have these little numbers right here. And so if we look at something like sodium, 11, sodium right here, that's written out as 1s2. Why? Because there's 2 in that first 1s shell. Then you got 2s2. Remember, the amount of electrons that can be in an s shell are given by 2l plus 1 times 2. Remember, we said that was the degeneracy. When s is 0, you get 0 plus 1 is 1 times 2. That's why you got the 2 there. 2s2. And then you get 2p6. And then 3s1. Right here. Again, L is equal to 1 there. 1 times 2 is 2, plus 1 is 3, times 2 is 6. So that's where the 6 comes from, right there. And you notice that we have filled up this shell, and we're just starting to fill up the third shell. And that's why it's the first item over here on the left side. Sodium is just right there, just beginning to fill up the third shell. Okay, and then sometimes they'll write this as neon. So they don't have to, this is neon completely filled up. You filled up the first, and then just add the 3s1. Okay, now when we did the Bohr atom and we looked at all the different energy levels, the n equals 1, 2, 3, and so on, we just said that the energies were all degenerate in here. But when you get to multi-electron atoms, if we get to, I don't know, just looking at lithium, what do we got? We got 2 electrons in the first shell, and then you got ones up here. Let's say that we got 1 up here in the second shell right there. The energy for all of the electrons that you pile into this shell right here don't all give you the same energy. The 3s can penetrate further into things below it than, say, the 3p can, and versus the 3d. These penetrate the least into it. These penetrate a little bit more. These penetrate the most right here. So the energy levels are not just dependent on n when you're talking about multi-electron atoms. It also depends on the structure inside. And if you follow, here I wrote out how the energy levels go. Here was our state 1 right here, n equal 2, but the 2p is slightly higher than the 2s right here. The 3s penetrates further than the 3d and a lot less more than the 3d. You notice how this is kind of working its way up this way. 4s, 4p, 4d, 4f right here. And this likewise 5s, 5p, 5d, 5s. So they all kind of go up this way because of the penetration in below. So now that we have that, now we can make up what's called the periodic table. I can either, well, since we're right here, we might as well do it right here. You'll notice when we start at the very bottom, we're going to start with, there's just 2 electrons right here that can be in this 1s state. So we'll just draw it right here. There's 2 of them right here. So this is the 1s state. And again, there's 2 possibilities because you remember L is 0, M sub L is 0, but M sub S can be plus or minus 1/2. So that's why there's 2 states right there. This is again what we get from just 2 times 2L plus 1. Okay, now we go to the next one, 2s, right here. There are 2 states in that. There's 2 in all of these right here. So we've got, right there, we've got 2s right there. So that's the next one right here. Then we come up, we got 2p. There are 6 states in that one. I'm going to draw it out here somewhere. I'll put it way out here. But it's on the same level as this one. This is the 2p. And there are 6 of them because there's, again, it's because it's 2l times 2l plus 1 times 2. And L is 1 for that. So there's the 2p. Then we go to the 3s, which is right here. 3s. Again, there's 2 states in that. 3s. Then we go to the 3p. Again, there's 6 in all of these. So we come over here. We come over here to the 6. This is the 3p's. 3p's. Then we're back to the 4s, which is right here. Yes, there's 2 of them. But you notice we don't go to the 4p next. We go to the 3d next. And there are 10 of them. Because this is 2. 4 plus 1, 5 times 2 is 10 right here. So there's 10 next right here. Let me just put it right there. There's maybe I'll move it over a little bit further. So that's the the 3D state. And there are 10 of them over here. Then you go to the 4p state, which there are 6. So that would be over here. 4p, and there are 6 of them there. Then we go up to the 5s. 5s. Then we go to the 4d. So I'll put it right underneath here. There's 10 of them there. 4d. There are 10. 5p. 6 of them over here. 6 of them. 5p. 6s. So we got 6s. 6s. But now we have 4f, which is 14 right here. Okay, I'll put that right here. Again, there's 14 because this is 0, 1, 2, 3. That's 3. That's 6 plus 1 is 7 times 2 is 14. That's the 4f. Then the 5d, which would be over here. 5d. Then 6p. 6 of them. 7s. Got 7s. Then 5f, which would be right here. 5f, 14 of them. 5d. There are 10. 5d. 6. No, wait. The 5d. 6p. Sorry. Let me just get where we're at right here. We had we're way up here. 7s, 5f, 6d. That's 6d. 7p. 7p, and there's 6 of them right there. Now, this starts to look like the periodic table. There's a few differences. They didn't, I guess they want to make sure it all fits on one page. So they take these two and just bring them down below. So I can squeeze that in a little bit more. And then also this one right here of helium. Since it's a completely filled shell and they like it to mix with every other thing that's completely filled, they'd like to put it on along with this last column. So they'll take this guy out of here, just chemically wise, and put him over here, just because he likes to mix with, because they're all filled up right there. Okay, and now if you just compare that to what we have up there, again, 1, 2, 2, and then we have all of these across, and then the 2 lines right here, they brought down to here. So we've got the whole periodic table right here. Now you'll notice trying to solve exactly what's going on quantum mechanically with a lot of these things is very difficult. They have a lot of approximation techniques and to help this stuff right here. Otherwise, it would just be too cumbersome right here. Okay, so now you know chemistry. Okay.